So again, starting with current electricity, we have already done this formula that electric current is defined as I equals to Q divided by T, right? So if you put this down in simple numbers or simple definition, that would be number of electrons flowing through an area in unit time. And the unit for this would be, or the SI unit for this would be A, which is pronounced as amperes. Can you hear me? Am I audible to you? All right. So current electricity, so the unit is A, amperes, right? Okay. And this is measured by an ammeter, which is connected in series, and the symbol is A. There is another instrument known as galvanometer, but the difference between galvanometer and ammeter is not that they measure different quantities, but basically the range of values. So the ammeter measures in milliamperes and amperes, and the higher values, of course, kiloamperes and megaamperes. But of course, the values of current cannot be that high. It's not practical. But high values of current are measured with ammeter, and very small values are measured with galvanometer. So usually values ranging in microamperes are measured with a galvanometer. Okay. But both of them are measuring current. The only difference of the name is based on their ranges. And this is connected in series. And if you're not familiar with a series connection, so basically there is only one path for the electrons to enter, one path for the electrons. So for an ammeter, the electrons have to enter in a circuit wherever they are connected. We'll get to that later. Wherever they are connected, the electrons have to enter from one terminal and have to exit from the other terminal, right? So that is how the ammeter will measure current for that circuit, right? And they have to be connected in series. There is another connection known as parallel connection, but that is for a voltmeter. That is for EMF and voltage and potential difference. That will be our next topic, right? So do we understand what is current and how we look at this? Right? Yeah. And a conductor would be assumed as an element that has free moving electrons to help conduction of electricity or electric current, right? Okay.
Yeah, so like if you have introduce an opposite charge, that's when
now we look at the direction of the conventional current. So conventional current moves from the positive terminal to the negative terminal, right? Although why do we say that it's conventional current? The reason is that it's an old belief. And since the whole electricity and the whole chapters and everything else, every concept has been based on this idea, we're just following something that's already been wrong, but it's accepted universally because it doesn't matter to the direction of current. It doesn't matter, it doesn't change the outcome of the question. So we have accepted this as a universal thing. Otherwise, the electrons actually, or the current actually moves from the negative terminal to the positive terminal, or you can say from an area of, or a terminal of abundant electrons to the terminal of where the electrons are less. So what is this conventional current? I'm going to draw a simple circuit and let's try to see or identify all the components. I'm sure that you might have seen this in your lower grades. So this is an ammeter that is connected in series. This is a simple resistor. Now, what is a resistor in real life? It could be any object around you that is consuming electrical energy. So be that your laptop, be that your mobile phone, tube light, bulb, fan, air conditioner, any object that is consuming electrical energy or converting electrical energy to other forms of energy, that will be referred to as a resistor. So even the electric heater that is in your house is a resistor, or can be modeled as a resistor, because they're consuming energy. So this is a simple battery or a simple cell, because if it's drawn in a single entity, we will call that a cell. If there are multiple cells, this will be called as a battery. And then we have a switch to safely turn a circuit on and off. So the longer terminal is the positive one, and the shorter one is the negative one. So positive, negative, positive, and negative, right? Right now the switch is open, or you can say it's in the open configuration. The circuit is not complete, the current will not flow. And when you close the switch and complete the circuit, when the switch is closed, where and how does the current basically flow? So the current, in conventional current, flows from the positive terminal through the ammeter, through the resistor, through the circuit, and then back to the battery. This is the conventional current. But the electron flow, which is discovered now, is actually the opposite of that. We say that it is going to start from a negatively abundant, or the abundant terminal, where the negative charges are more in number, go the opposite route to the conventional current, and then come back to the battery in this way. So this is referred as electron flow. And current does flow in this way. But since when they were discovering this chapter, discovering all these quantities, at that time scientists believed that it's moving from positive to negative. That's what we are still following today. And in every circuit in physics, in every place in physics, be that higher level, lower level, wherever you go, you will be assuming conventional direction of current unless asked or stated otherwise by the examiner. And it's very rare that the examiner would confuse you with an electron flow. I've only seen an MCQ in the past papers in which he asks you the conventional flow and the electron flow through the resistor. Students forget about the fact that he was not asking about the battery, he was asking about the resistor only. So anyways, so do we understand what the conventional direction of current is, from positive to negative, and that's how we're going to assume, right? Okay, so now we have a small comparison between a DC current and an AC current. So DC is referred as direct current, and AC is referred as alternating current. So DC, basically, for your knowledge and information, any cell, any battery, that could be for UPS, could be for let's say from a capacitor as well. So all these sources provide, even rechargeable batteries of your phone and the laptop, all these sources provide direct current or direct electricity, or you can say a current that is always going to be in one direction only, and it is represented by a symbol that is already discussed and drawn over there. So that is positive and negative, and the direction of current will always be from the positive, let's say, to the appliance, and then back to the battery. This is the symbol of a simple bulb, basically. So that is how the current is going to flow forever, or until the time the battery has some energy to offer. That's how the current is going to flow. So since the direction is not changing for the current throughout its lifetime, wherever configuration that is connected, we consider this to be the direct current. Then we have alternating current, that actually is received from AC generators. That will come in the syllabus of grade 11 after this topic, and then magnetism, and then we're going to move towards AC current, how it's actually produced in the first place. But when it is produced, the output actually looks like this. The current is sometimes positive, sometimes the current is negative. So I'm going to draw two colors. So the positive cycle is referred as the red one, and for the sake of discussion, let's refer to the negative cycle as the black one. So in a circuit, for example, the symbol for AC electricity is represented as this way, right? And then we have a simple switch you can connect. We could have a simple resistor, and then the circuit is completed in this way, right? So when there is positive current, the current will flow something like this. For the sake of assumption, we're considering that the current is going to flow like this through the circuit. But when there is a negative cycle or the negative current, the current will flow opposite to this. So for some duration of time, the current is flowing clockwise, and for some duration of time the current is flowing anti-clockwise, but the durations are basically equal. For your level, the durations will be equal. So if it is flowing clockwise for 1 second, it will start flowing anti-clockwise for 1 second. So that is how AC electricity or alternating current is moving through the circuit. But if I analyze the electron itself that is carrying this electrical energy, that's quite interesting. So if I just look at this conductor by zooming into that, I'm only looking at the conductor for an AC electricity. What's happening with the electron? The electron, let's say, is this charge. So sometimes it's moving towards the left side when it was positive, or the clockwise current as represented by the red arrow, and sometimes it's moving towards the right side as represented by the negative arrow. So basically the electron itself is oscillating between two fixed positions. Now this is just one electron. What about the others? So what's happening is that these electrons all move together in this way and then start moving in this way, just like the longitudinal wave particles. Do we remember how those move forward and backward, but never really leave their own position? So something similar is happening when AC electricity or AC current is flowing through the circuit. Charges are moving forward and backward, never really leaving their own position, right? And when you go to A levels, this topic will be known as simple harmonic motion. Oscillation of a system, periodic oscillation of a system, is known as simple harmonic motion. But anyways, you'll get to that later. So, but do we understand deep down how the electrons are actually moving for AC and how they're moving for DC? For DC, they have to complete one loop. When one electron leaves the battery, it has to complete the circuit and then go back to the battery. For AC, they are moving on their own position and exchanging energy because the source or the battery is forcing them to do so in the first place. And when that electron moves through the resistor, it dissipates energy, and that's how we're using electricity in our appliances and in our homes. Do we understand this point?
Yeah.
So alternating current,
so in alternating current, the direction will change at equal intervals.
yeah. And for DC, the current is not changing, right? So for AC electricity, there is no direction for conventional current. It's meaningless because the current is moving in both directions. So we don't say the direction of conventional current in AC. We only say direction of conventional current, or it only exists in the area of DC, right? All right. So we have learned the distinction between DC and AC as well. This is important in terms of your O-level syllabus and A-level syllabus. I have seen this question many times. He would ask you to distinguish between them, and you will only have to distinguish between them in terms of motion of electrons, right? Okay. We did do this idea that the ammeter has to be connected in series. Okay. All right. Now the next concept is quite it's interesting for me, but I've seen students struggle with it. Sorry. But if you don't understand this right now, it will forever create a problem for you for the next incoming syllabuses and of course higher studies. The concept is voltage. You may have heard this word in your daily life, but what is voltage? You see, current is the flow of electrons, is the number of electrons, is the number of workers you've hired in a circuit to do something for you. Simple as that. The quantity of electrons that are in that circuit doing something for you. Okay, fine. Then what's voltage? Voltage is the energy of that electron. Energy per electron. And of course, since we're not looking at the electrons individually, I will say energy per unit charge, or the packet of electron. That would be more convenient for me to look at, because the energy contribution or the energy carrying of one electron would be very small in number. And again, we are running away from, or you can say we're trying to avoid mathematical inconveniences. So again, we are going to go back to the charge, right? The universal formula for voltage or potential is V is equal to work done divided by Q, work done divided by charge. Now, since the unit of work done is joules, I write this down as joules per coulomb. Energy has the same unit, that is joules. So the actual definition is work done by the charge. But how I explain this to the students is the energy spent by the charge or energy carried by the charge in its own right from one point to another. So current is the number of people or the number of electrons working for you. Voltage is how much energy is possessed or is how much energy each packet or each electron is capable of delivering. And of course, electrons don't have their own energy. They're going to take that energy from the battery. So whatever energy the battery is going to provide, they're going to carry from one point to another and then come back to the battery as well. Now, to distinguish between the types of voltage, it's only a matter of perspective, how we look at this. So the first type of volt, do we understand what's voltage? That's the energy of the electron. Simple as that, right?
So it's basically work done, which would be energy per how many electrons are passing.
Yeah. How much energy each electron carries, or how much energy or how much work done each worker can do for you when it moves through a circuit. Simple, right? So there are two aspects of the electron. The first one is the number of electrons as current. The second aspect is the energy of electron, that is voltage. Now there are two types of voltages. Mainly the distinction is purely based on perspective and purely based on purpose. So the first one is EMF. I just discussed that in the previous lesson as well. So EMF is electromotive force, again measured in voltage as V. The second type of voltage is potential difference. Potential difference, and mainly referred as PD, and again measured in volts. Since both are representing the same quantity but from different aspects, they have the same unit. Okay, so what is EMF? EMF is basically any energy or any form of energy converted to electrical. So anything in the universe that is converting any other form of energy into electrical, we will call that object or that element as one of the sources of electrical energy. So if I look at the cell, or if I look at the dry battery, or if I look at the battery itself, I see that there are chemical processes happening inside the battery, right? So that chemical potential energy is turning into electrical energy when I extract it from the battery, right? So if I look at the wind turbine, wind energy is being turned into electrical energy, of course by some complicated procedure inside the machine, inside the motor as well. But then again, that is also going to be treated as a source of EMF, right? Because it is converting some other form of energy into electrical energy, purely in the form of electrical energy, which I can extract. Potential difference, however, is for those elements in the circuit that are converting electrical energy to other forms. So, any other form. If I look at my electric bulb or tube light, that is converting electrical energy taken from the source into light and heat. If I look at the electric heater, it is converting that electrical energy into heat or thermal energy. If I look at the air conditioner, it's converting that same electrical energy into thermal energy by absorbing thermal energy from the environment. And similarly, if I look at an electric vehicle, it's converting that electrical energy into motion, right? So electric motor, of course. So all those appliances around us that are taking in electrical energy, converting into other forms, those appliances or the voltage of those appliances will be referred as potential difference, and those who are actually providing electricity or converting everything else into electricity, they will be known as EMF. So one more summary of this distinction would be that EMF is going to come from the source. Potential difference is actually the consumption of an appliance. So simple as that. EMF is the energy provided by the source. What did the source invest, or what did the source give to the electron so that it can distribute that energy to other parts of the circuit? Potential difference will be measured across the appliance or the load. How is it going to be used? Where was it used in the first place, right? And potential difference is measured by a voltmeter, which is connected in parallel to that respective appliance, right? So, and a parallel connection would mean many paths or multiple paths, many paths for the electron to move either across it, bypass it, or move through an entirely new path. Depends on the electron. We'll get to that later. So
And both of these are measured in voltage.
yeah,
So that
both of them are measured
it
in
just
voltage.
defines how much energy is being converted because
Yeah,
voltage is
yeah.
the energy.
If I'm looking at the EMF, that is the voltage of the source, I would be defining it in this way: how much energy is being provided by the battery to each coulomb or each packet of electron. When I look at it from the potential difference perspective, I will be defining or describing it as how much energy is being converted or is being used up by that resistor when one packet of electron moves through it. Right? Okay, there is one other distinction with EMF and voltage. We get to that in this diagram. So let's say I have a battery, a, a circuit, and a resistor, for example. Now, for the sake of discussion, I'm connecting two voltmeters, one on the source and one on the resistor. These are voltmeters connected in parallel. And when I say they are connected in parallel, how do I define this? You see, when current actually comes at this location, the current has two choices. It can either go through this circuit or it can either go through this circuit. The moment the current is going to have a choice to divide itself into two or more branches, we will call that circuit to be a parallel circuit. Do you understand this idea? Right? For the ammeter, we didn't have that choice. So if that was over here, the ammeter would be connected over here by completing the circuit. So we can very well see that when the electron actually approaches this terminal, it cannot bypass the ammeter or go around it. It has to go through the ammeter to the other side of the circuit. So this configuration will be known as a series configuration, and the other one is known as a parallel configuration. And you have to remember this, that the ammeter will always be connected in series and the voltmeter will always be connected in parallel. Alright, so the next idea or the next aspect of this would be that, let's say for the sake of discussion, that the electron actually exits from the battery, right? Some energy is going to be used by this wire because it's a resistor. So for the sake of discussion, I say that it uses approximately 2 volts or 2 joules from every packet of electron for the electron to move from one point to another. So whatever energy the electron may have at this location, it will have 2 volts less when it reaches this point, right? So do we understand this point? Because wire is also a resistor, it will also take up some energy. Under ideal circumstances, we assume that the wires don't consume anything, but they do. In real life, they do consume something. Okay. Now, for the sake of example, I say that the resistor that I'm using right now needs 10 volts to function properly. Or you can say it will demand 10 joules of energy from every electron or from every packet of electron to function properly. Could be a bulb, could be a fan, could be any object or any appliance that we're using right now, right? Okay, so the electron comes at this point, loses further 10 joules of energy while moving through it, and then goes back spending the same amount of voltage or same amount of energy per unit charge as it did when it actually came to the circuit, and then reaches this point, right? So can you tell me how much energy would you spend or would you give to this electron before it starts moving in the circuit? How much energy should it have before it starts moving in the circuit? Right now at this point it will have no energy, completely drained when it reaches or goes back to the battery. How much energy should it have when it actually leaves the circuit so that everything happens smoothly?
So if you add up all the energy that needs to be used for it to be able to actually complete the circuit, so then it'll just have to be above 14 volts.
Above 14 or 14, for the sake of discussion, let's keep this at 14, right? Of course, a bit more than that would be a good option, but again, if you provide more voltage than the appliance or more energy than the appliance, it may run the chance of burning it, right? And we can't do that. We have to be very careful about that.
So if we have less than 14, then the energy will also mean the electron won't complete the circuit, it won't finish moving through.
They would finish moving through it, but they will not be able to turn the appliance on. The current will be flowing through it, but the bulb will not be switched on, although the current will be flowing through it. Although the current will be flowing through it, how much effort does the battery need to put in so that the appliance runs effectively or runs smoothly, and the energy consumed in the wires can also be compensated for? right? And if I look at the potential difference only, I am not concerned with the rest of the circuit. I'm only concerned with my appliance. Is my appliance getting the energy that it requires? If it is, then I will say that this is potential difference. So I see potential difference from this voltmeter, and I will see EMF from this voltmeter. Now let's see what the voltmeter is actually doing. Voltmeter is actually doing a simple calculation. It's trying to measure how much energy does the electron have when it entered one terminal and how much does it have when it exited the terminal. So for example, when the electron enters from this terminal, it exits the battery at 14, reaches this terminal at 12, and loses 2 volts through this transmission wire. So when it enters this appliance, it is going to lose 12 joules further, and when it reaches the exit terminal, it will have 2 joules per coulomb. When it transfers through the wire again, it will have nothing left. Basically, the electron will be at this location, but for the sake of discussion, I'm drawing it on the outside so that I can draw the voltmeter accurately, right? Okay, so when it reaches at this point, it has nothing left or nothing to offer. So when the voltmeter actually makes this calculation, how is it actually looking at? So the voltmeter actually taking the difference of both readings. So it's measuring this voltage, he says, or it actually is doing 12 minus what's the energy content of the other terminal. The electron, when it exited, had 2 joules. When it entered, it had 12. So 12 minus 2 is equally 10 volts. So this appliance that I'm connected across must be consuming 10 volts, or is must be consuming 10 joules per coulomb when the electron actually moves through it. But when we come towards the other side of the pond, we see that one terminal has 14 volts and the other terminal has 0 volts. So what is the difference between the energy content? So that is 14 volts. That is what the voltmeter actually shows you. So in my example, the potential difference would be 10 volts only across my appliance. And in my application, the EMF will be 14 volts that I'm trying to measure to find out how much effort does the battery need to do so that my appliance runs successfully, no matter the cost, no matter what's in the way, right? So it's possible that the transmission lines take up, let's say, 3 volts or 5 volts, whatever that is. So that's actually, let's look at the larger aspect of this. So that's actually what's happening in daily life. You see, when the electric supply company generates electricity, there are a lot of things in the center as well, but I'm going to skip all of that. When the electric supply company actually generates electricity, now you are getting electrical supply at 110 volts, right? Do you think that the transmission line that they've connected between you and your house is error-free, or is energy content-free, or is loss-free? No, it's not. So what they're going to do, they're going to calculate the resistance of the wire, they're going to calculate how much energy it requires, or it spends, or it consumes. Let's say every section consumes 10 volts of energy, right? And this is your house, and you want the electrical voltage to be 110 volts. So what they're going to do, they're going to pump in electrical energy at least 130 volts, so that when the electron actually starts traveling, it has 130 volts. When it reaches at this point, it will have 120. When it reaches at this point at your house, it will have 110 volts. So they deliberately calculate all of these. That's why the concept of EMF is necessary, because we want to know how much effort does the source need to do or need to make in order for me to get a successful voltage that I have used or I'm going to use for my appliances. Do you understand? Now, the 110 volts that I'm going to get at my house will be the potential difference, because my house is a resistor. And 130 volt that I'm getting from the generating station will be treated as EMF, because that is the source. And one more aspect, EMF will always be greater than potential difference. It will always be greater. We always need to give more energy than the required value, because we know that some of the energy is going to be lost in the transmission. Do we understand this point? And please do not forget about this idea. This is very important in terms of your higher education. One more aspect in terms of simplifying this further. Whenever you encounter voltage, always think about the fact that this is energy. It will be consumed by that respective electron, by that respective appliance, by the respective load. So in the incoming topics that we're going to solve, we're going to look at multiple